So today we are starting off with the Cambridge IGCSE Physics 0625 Paper 6 Specimen from 2023, and this is a 40-mark paper, 1 hour time, and it has 14 printed pages. So we just go ahead and check. We've got all 14 of them. Yes, we do, including the blank pages. Right, and that all of them are printed. Obviously, you'll be opening a paper when you are asked to do so during the examination. So here's question 1. A student investigates the rate at which water cools. The apparatus is used as shown in figure 1.1. So you have water in a beaker, the lid partly covering the beaker. You've got a thermometer dipping into the water. So here is an enlarged image of the reading on the thermometer. Read and record the room temperature theta R shown on the thermometer. So what can you read off of this?
Could you? In the thermometer shows 20.
Is it 20?
Wait, could you zoom out? I want to see the whole question. Uh, Wait. Let me see.
You just need to take the reading of the thermometer image.
Yeah, I'm trying to zoom in.
I'll zoom in.
23 degrees Celsius.
20 how much?
3 degrees Celsius.
It's not
23.
it's not 3 beta. Look at that. Look at it carefully.
Are we gonna read the red side or the white line?
The black lines.
Yeah, so it's 21.
Yeah,
21.
21.
Yeah.
Okay, so we write, get our pen, just position this comfortably. And so we have 21 degrees centigrade. Okay. So a student pours 100 centimeter cube of water, hot water, into a beaker. She
Okay.
places lid A on the beaker. This leaves half of the top of the beaker uncovered. She records the temperature of the water in the beaker and immediately starts a stopwatch. She records the temperature theta of the water every 30 seconds. Her recordings are shown in table 1.1. Right, so this. Uh, she repeats the procedure using lid B. This leaves a quarter of the top of the beaker uncovered as shown as figure 1.4. Okay. Now complete the heading rows in table 1.1. Complete the time column. So time, what they're missing are the units. Whenever you make a table, as I mentioned to you, right, you need to put in the what it is that you're measuring and the unit in which you're measuring, right? So
Would be time per second.
time per second, and theta is for temperature. So what will be the unit here?
B.
Degrees centigrade.
Yeah. Right.
And degrees, not just C, right? If you just write C, that could be charge, coulombs, right? It could be
Yeah.
something else, right? You got other C's. So degree centigrade, right? Okay. Now you need to fill in the column for time. So it mentions over here that she's recording temperature every 30 seconds. So how do we fill this in?
30,
Yeah.
60, 90, 120, 150, and 180.
Describe a precaution that should be taken to ensure that the temperature readings are as accurate as possible.
Mm, Dating
Hmm?
or wait for stabilization.
Stabilization when? Because during the experiment you can see the temperature is dropping, so nothing's going to be stable. If you're waiting, you'll miss the proper reading.
So, like, okay, we should avoid the parallax error.
Okay, now since you mentioned that, it is something given in avoid parallax error. But what does that mean? So what would you do? So in the marking they mentioned that if you're giving parallax error as a precaution, then you need to detail what to do to avoid it.
Okay, so you have to read the thermometer scale at the eye level and perpendicular to the liquid column.
Right? So this is what would get you your mark. Right?
Okay.
Just saying avoiding the parallax error is not good enough because that's too common a statement. Now, the other thing that they suggested, for example, is wait for the temperature. The one thing you said for stability in temperature, and asked you
For the
at
stabilization.
yeah, and so I asked you like at what point, because you can't wait for that during the experiment. The value will change if you're waiting for it, right? And so
Yeah,
wait until reading stops, right? For the
or
reading,
falling.
no, wait for the reading to stop rising, right? At start of experiment. So when the experiment is starting, you wait and you see that you're starting off with a stable temperature, and then you start timing. Because for example, when you're starting off and you see it's 80 and then you start timing it, and after 30 seconds it's like 80.3, I'm like, how did it go up? So obviously that's going to mess with your results,
Yeah.
right? So you start for the temperature to become stable before starting your time.
Mm.
So that's another thing you could have said.
Okay, so like, but if you write avoid
Yeah,
parallax,
with the explanation of how to do it.
you have to write it with the explanation so that you
Yes,
just don't lose the answer.
yes, yes.
Okay.
Okay. Write a conclusion to this experiment stating for which lid the rate of cooling is greater. Justify your answer with reference to the results. Okay. So lid A had the half open, lid B had the quarter open. Right? Now, note, tell tell me by from these observations which the water is cooling faster.
Which water is cooling faster?
Yeah.
Zero? At zero, like with lid A?
Overall, right, the beaker with lid A starts from 80, and in 180 seconds, that's 3 minutes, right, goes down to 68, right? So there's a difference of how much?
No,
Uh,
wait.
12 degrees, right?
Yeah.
There's a difference of 12 degrees centigrade. Over here, you start off at 81 and you go to 73.5. So you have a difference of 7.5 degrees centigrade. All right, so which one's cooling faster?
Lid B.
Eh?
Lid B.
Lid A. Lid A went down by 12 degrees. Lid B went down by only 7.5 degrees.
I didn't get that.
Which temperature did you start off with? 80.
Yeah.
Which temperature did you have after 180 seconds? 68.
Yeah.
That is a difference of 12 degrees centigrade, and you're losing heat, so the temperature is going down.
Okay.
With lid B, you started off at 81, and after 180 seconds, you are at 73.5. That is a difference of
Oh,
only
okay.
7.5 degrees centigrade.
Okay, okay, I
So
got it.
which one is cooling faster?
The lid A.
Lid A, right?
Yeah.
So that's one thing. So write a conclusion to this experiment stating for which lid the rate of cooling is greater. So again, you can write it as bullet points. Beaker with lid A
Has a rate of cooling greater.
cools faster,
Yeah.
right? Uh, with a change of 12 degrees centigrade over 180 seconds, right? And
Whereas
so,
for lid B, it only dropped by 7.5 degrees.
right now they're asking you to justify your answer with reference to the result. So, right, for lid B, it cooled only 7.5 degrees centigrade in
Yeah.
180
Seconds.
seconds, right? Now you could argue, well, it was hotter. Yeah, but by 1 degree, that's not going to make a big difference,
Yeah.
right? It's like, oh, well, you started hotter, and so yeah, okay, fine, right? But 1 degree centigrade is not going to make a huge difference, right? And so you can also refer, for example, between 30 and 90, right? Or you could say, right, between 30 seconds and 60 seconds, lid A went from 77 to 74.5, and lid B went from 79 to 77.5. So you can refer, because they ask you to refer to the results.
Yeah. Okay.
Over here, because we don't have enough space in the lines to make bullet points, we're just using sentences, right? Just make your full stops clear. Between 30 to 60 seconds, lid A went from 77 to 74.5, and lid B, so you can write whereas from 79 to 77.5,
Okay.
and you get your marks.
Yeah.
Okay. Suggest a change to the apparatus that produces a greater difference between the rates of cooling for lid A and lid B. Explain why the changes produce a greater difference. So, right, here are the lids. What will you change to produce a greater difference?
Start with higher initial temperature for the water,
You
or
need to make a change to the experimental apparatus.
okay. Use a thinner material for the container.
Use a thinner material.
Yeah.
Okay, that can work.
To ensure, so that we can be sure the lid's performance is the main factor being measured rather than the
Oh
beaker's.
no, it doesn't matter. Like, you need to make the difference greater. So it's not the performance of the lid. So,
Oh,
right, uh, use a thinner material for the water container. Now you need to explain how this is going to produce a greater difference. Right? If the material is thinner, what will happen?
well, how will I? Okay. Mm,
Remember Unit 2, thermal energy and
The
trans.
oh, okay, wait. So like the difference in heat loss through the lids.
Again, it's not just about the lid, it's about any change to the experimental apparatus, right? So it's not focused on the lid. It could be the lid, it could be something else. You said that use a thinner material for the container.
Yeah,
How is that going to help produce a bigger difference?
a better insulator or like smaller surface area reduces the background heat loss.
That's something different. Do you want me to erase this?
Yeah, it is that. Okay.
Okay, just let me tell you, if you were using this, the explanation would be that heat loss via conduction would occur more easily. Does this make sense?
Yeah.
Okay, so that's the explanation you could have given. Now, what's the explanation you're giving now? Use an
Use a container made of a better insulating material.
use container made of better insulating material. And so, what's the explanation for that?
Better insulator reduces the background heat loss from the sides and the bottom of the container.
Right, so it reduces background heat loss. Okay, all right. So another student thinks that the cooling rate is directly proportional to the percentage of the surface area uncovered, right? So how much of the lid is open, like the uncovered area, the more the uncovered area, the more the cooling. It's directly proportional, right? He draws a graph of cooling rate against the percentage of uncovered area to investigate this. Describe how his graph line shows whether the rate of cooling and the percentage of uncovered surface area are directly proportional. So what are the features of a graph that show direct proportionality?
Uh, a straight line on the graph,
All right, so the graph will be a straight line.
and it should pass through the origin.
Good. Students in other countries are doing the same experiment. State one factor they must keep the same to obtain similar readings. So what should be constant?
Initial temperature of the water,
That could be one thing.
or volume of the water.
Obviously, you need to write only one of these. You could also have,
Room temperature.
yes, at which, because that's going to affect heat loss.
Yeah.
Okay, it could also be the material of the beaker, or the size of the beaker, or the type of the beaker, or the lids. So it could be some of that stuff as well. Anyway, good on that. Oh, we've got a bit of electricity coming in. All right, a student is investigating a resistance wire. She uses the circuit shown over here. All right.
Yeah.
So right? On figure 2.1, so you got the power supply, you got an ammeter, this is points P and Q, and this is the length of the wire. The length of, because this is right flexible, you can place the crocodile clip. The crocodile clip has metallic teeth, and so you can place it at different lengths of the wire. And as you know, right, there is a relationship between length of wire, right, and resistance. Remember that relationship?
Yeah.
What is the relationship between the length of wire and resistance?
Actually, I would like a brief on.
Huh?
I would like a brief on that.
It's directly proportional, right? So the longer
Yeah.
the wire, the greater the resistance.
Yeah. Okay. So
So on figure 2.1, draw a voltmeter connected to measure the potential difference across terminals P and Q.
since it has a short wire, it will have less resistance between P and Q. No, wait, actually, it has greater wire. Okay.
So to measure the potential difference across P and Q, it says over here that you need it to be in parallel with P and Q.
Yeah. Yeah. Okay.
Okay, the student connects the crocodile clip to a length of 90 centimeters of the resistance wire and measures the potential difference V across the terminals P and Q, right? And the current I. So we need this reading. So this is like, what's the reading over here?
2.6.
Yeah. So this is 2.6 volts. And what's the reading over here?
Uh, 0.8.
No, 0.36. Right? So each small division is 0.02. So 0.22, 24, 26, 28, 0.3, 0.32, 0.34, and 0.36. So read and record in table 2.1 the values of V and I shown in figures 2.2 and 2.3. Right? So V is what now? 2.6, and I is 0.36. Right? And then you need to calculate resistance. So, right, R is V over I. So, what's the resistance? Do the calculation.
Yeah, that's what I'm doing. Okay, so the it will be 7.2 for R divided by what's that sign? It is gonna be 7.2.
Just a second. Complete the column headings. Oh, sorry. So, the student then connects the crocodile clip to 60 and 40, She measured the potential difference across turners P and Q, and the current I readings are shown here. Complete the column. So what is the unit for voltage?
Wait, 7.2
Unit, SI unit.
V.
And for current,
A.
so that gives you 1 mark. Okay. Calculate and record in table 2.1 the resistance.
Are we gonna, fill in
Yeah, so
the
that's part C1.
oh, okay, okay.
Yeah, so what's the resistance over here?
For the first row,
Yeah,
0.080.
2.6 divided by 0.36.
Yeah.
Isn't it 7.2?
Oh, okay, you're talking about this one. Okay, yeah, 7.2. Yeah, yeah. Okay. Yeah, 7.2. And for 2.5 and 0.49, it's gonna be 5.1.
Yes.
And the next one is gonna be 3.1.
Okay, so that's done. Calculate and record in table 2.1 the value of R over L for each length. So divide 7.2 by 90.
Yeah. So it's gonna be 0.080.
0.080.
Ah, look how smart. Okay. 0.085.
0.085.
And lastly 0.078.
0.078. Right, so those are correct.
As usual.
Uh-huh. Another student suggests that the values of R over L for each length of wire should be the same. State whether the result supports this suggestion. Justify your statement with reference to values from the result. So looking at this, are they the same?
The word? Could you repeat yourself?
Another student suggests that the value of R over L for each length of wire should be the same.
Same. Okay.
State whether the result supports, so whatever ratio you're getting of resistance to length,
Mm-hmm.
you're going to get like a constant value. You're going to get the same value. State whether the results that you've achieved support this suggestion. So whether you think that looking at this, what the student is saying is correct, that you're going to get more or less the same value. Justify your statement with reference to values from the results. So this is 1 mark. So
Um. Wait. Wait. It shouldn't that mean that the resistance is directly proportional to their length?
the resistance is directly proportional to the length, but if you take a ratio of resistance to length, you're going to get like a constant value.
Yeah.
So are you getting that constant value?
Yeah.
You are, right?
Yeah.
And so the statement is that the results support the suggestion. Justification. Now, you need to justify this. Why? Because it's 0.08, 0.085, 0.07. So how are you going to justify this?
The well. Okay. The values of R to the L are too different to be considered constant.
Huh?
They are too different to be considered constant.
But you just said that the statement is being supported.
Yeah. Do not support. Sorry. Do not support.
Okay, now here's where I'll tell you. It is being supported.
It is.
Yes. So what you're observing over here are experimental differences
Okay.
or variations, right? And
So they
what,
are within the limits of the
yes,
experiment.
yes,
Okay.
exactly, right? So justification would be that the variation in results are within the limits of experimental accuracy. Right? Accuracy means how close the observed, like the observed value is to the actual value. Right? So they're close enough. Right? That's what
Yeah.
accuracy means.
Yeah.
Remember, reliability, there are two terms you need to know. You need to know accuracy, right, which is how close a result is to the actual value. And then there is reliability, right? And that is, can you get the same result, close enough, obviously, not exactly the same, but the same results on repeating the experiment. Okay?
Yeah.
So over here we're talking about accuracy. Right? It's close enough, it's good enough.
Okay.
All right. Suggest one difficulty which explains why different students doing the experiment carefully with the same equipment may not obtain identical results. Right? So again, one difficulty which explains why different students performing the experiment carefully. Now this is
Uh,
important. They are doing the experiment carefully, so you cannot say, oh, they made a mistake. No. You need
they.
something,
Yeah.
you need something
So
that is a problem with the setup.
yeah.
So look at the setup. What could be a problem?
Uh, Ensuring that the wire is perfectly straight.
Straight for
Sorry.
the for the length.
Yeah.
Huh. We
Or
could do better than that.
parallax error when
No,
reading the
no,
video.
no. There's nothing to do with parallax over there.
Okay. Changes in temperature.
Uh, look at the circuit set.
Difficulty in placing the contact or crocodile clip
Yes,
exactly on the mark.
yes,
Look how smart.
good.
Oh my God,
Right.
thank you.
So difficulty in placing crocodile clip at precise location, at precise point. Right. Another thing that is suggested is the connection, right? The contact between the wire and the crocodile clip is not precise. And another that they mentioned is difficulty in measuring wire length. So you're just like, you'll be like, I said that, but no, it's slightly different. Length to nearest millimeter.
I'm still gonna say I said that.
Okay. A student finds that during the experiment, the wire becomes hot because there is a high current. he decides to use a variable resistor to prevent this. Draw an X on the circuit to show where a variable resistor is connected for the purpose of the experiment.
Hmm. Uh, so I should be marking X anywhere along the main loop of the circuit.
Yeah.
That is not parallel with the another component.
Hmm? Yeah.
Uh, okay. So, I mean, you tell me where should I do it?
All right, let's
Mm,
put it over here.
Isn't that okay? Can't we put that in the resistance wire?
Oh, no.
No?
No.
Okay.
In the space below, sketch the circuit symbol for a variable resistor.
Wow. We should first draw a rectangle. That is a symbol for fixed resistor.
Yeah.
And draw a diagonal arrow starting from the bottom left and pointing to the top right.
There you go.
Is that correct?
Yes.
Okay.
All right. So that was just those are two questions. Okay. So we have this question over here that has to do with light and waves and stuff. And
Okay.
then, all right, to make a graph. And then is the dreaded planning question.
Oh God.
Yes, well, once you do enough of these, you get an idea of what there. There's like a pattern to this. Okay.
Mhm.
So once you get used to it, you do enough of these questions, you understand the pattern. You're like, oh, I know I need to mention this, this, and this, and this. Right? It's just that the scenario changes, but the underlying concept and the approach remains the same.
Yeah.
Okay.
Yeah.
So yeah. So how about we continue this the next class
Yes.
from question 3 onwards?
Yes. Definitely.
Okay. So I'll see you next time, inshallah.
Okay. Allah Hafiz.
Please.
Um. I